All right, let's dive into the world of aldehydes and ketones. These guys are seriously some of the most fundamental building blocks in all of organic chemistry, showing up in everything from perfumes to plastics. So let's get right into it. But before we get bogged down in all the heavy chemistry, I've got a question for you. What on earth could possibly connect the lovely, nutty smell of almonds with the, really sharp preservative smell of formaldehyde they use in biology labs? I mean, they seem like they're from completely different universes, right? But believe it or not, they share a core chemical feature. And the answer is the carbonyl group. You're looking at it right here. It's really just a carbon atom with a double bond to an oxygen atom. And this little group, it's the heart and soul of both aldehydes and ketones. So what's the difference? Well, it's super simple. If that central carbon is attached to at least one hydrogen, boom, you've got an aldehyde. But if it's sandwiched between two other carbon groups, then it's a ketone. See? Simple as that. Now, to really get why these molecules are so incredibly versatile, we've got to look at their architecture. The shape and the bonding of this carbonyl group, well, it dictates pretty much everything about how it behaves and reacts. So what's so interesting here is the geometry. That central carbon atom is what we call sp2 hybridized. All that really means is that it forms this flat, triangular shape with the atoms it's bonded to. This gives us what we call a trigonal planar structure, with these perfect 120-degree angles. And because it's so flat, it's very open and, accessible for other molecules to interact with. Okay, let's break down that double bond a little more. First up, you've got the sigma bond. Think of that as the strong, direct, structural link between the carbon and the oxygen. Then you have the pi bond. This one's formed by the sideways overlap of some other orbitals called p orbitals. A good way to picture it is like a cloud of electrons just sitting above and below that main bond. And it's this pi cloud that makes the double bond so darn reactive.
So here's the absolute key. Oxygen is more electronegative than carbon. It's just a bit greedy for electrons. This means it pulls those shared electrons in the bond towards itself. This tug of war creates what's called a dipole, which you can see on the slide. The oxygen becomes a little bit negative, and that leaves the carbon a little bit positive. And that positively charged carbon, it's basically a giant target for other molecules to attack. This right here is the secret sauce of carbonyl chemistry.
Okay, so now that we get their structure and why they're so reactive, the next obvious question is, where do they come from? How do chemists actually make them? Well, if we zoom out a bit, there are two main types of starting materials we can use, alcohols and hydrocarbons. Let's kick things off with alcohols. This is probably one of the most common ways to make aldehydes and ketones, whether you're in a research lab or a giant industrial plant. In a typical lab, the go-to method is oxidation. And the rule here is just so straightforward and predictable, which is great. If you start with a primary alcohol, and that's just an alcohol where the carbon with the OH group is attached to only one other carbon, you oxidize it and you will get an aldehyde. Now, if you start with a secondary alcohol, its oxidation is going to give you a ketone every time.
Now, for big-time industrial production, they often use a different method called dehydrogenation, especially for alcohols that turn into vapor easily. You basically pass the alcohol vapors over these hot metal catalysts. This method is usually way more efficient and makes fewer messy byproducts than oxidation, which is why they love it for large-scale stuff. But guess what? The same rule applies. Primary alcohols give you aldehydes, and secondary alcohols give you ketones.
All right, let's switch gears to our second category, making these from hydrocarbons. These methods are all about either breaking or adding to carbon-carbon double or triple bonds to create that carbonyl group we're after. One really cool and powerful reaction is called ozonolysis. So you take an alkene, that's a molecule with a carbon-carbon double bond, and you react it with ozone, O3. The ozone pretty much acts like a pair of molecular scissors, just snipping that double bond right in half. The really critical concept to get here is that the products you end up with, whether it's two aldehydes, two ketones, or one of each, depends completely on the structure of the alkene you started with. So what about alkynes with their carbon-carbon triple bonds? Well, by adding water across that triple bond in a process called hydration, you can also make carbonyl compounds. And this gives us a classic rule and exception situation. The general rule is hydrating almost any alkyne gives you a ketone, but, and it's a big but, there is one very important exception. The simplest alkyne, ethine, when you hydrate it, you get acetaldehyde, which is an aldehyde. Whew, we have covered a lot of ground, haven't we? We've looked at the structure of the carbonyl group and 4 totally different ways to synthesize it. So let's bring it all together and create a final summary map for you. From 4 different starting points, using 4 different reactions, we end up at the exact same place, the incredibly versatile and reactive carbonyl group. So here it is, your synthesis toolkit. We've seen how to make carbonyl compounds from alcohols using both oxidation and dehydration. And we've seen how to make them from hydrocarbons using ozonolysis and hydration. Each of these pathways gives you a different route to create the specific aldehyde or ketone you might need.
We've seen today how that flat geometry and that polarized bond of the carbonyl group directly lead to all of its characteristic reactions. This fundamental link, this idea that structure determines function, isn't just for carbonyls. It's a theme that runs through all of chemistry. So the final question I want to leave you with is, where else in the chemical world do we see this incredibly powerful principle at play?